Hello, good evening, students. Welcome you all for the second session on states of matter. Okay, in first session we learned about uh, yeah. Sorry for the delay, and hope you are all able to hear me properly. Yeah, in the first session we discussed about gas laws mainly, and we also studied about various states of matter. So we learned what are the two opposing elements existing in the any matter, yeah, which makes them either in solid phase or in liquid phase or in gaseous phase. One is intermolecular force, which I also told can be called as van der Waals force or hydrogen bond, and then there is the uh, thermal energy, which is the opposing element. So thermal energy tries to make all the molecules go apart, and intermolecular force or the force between attraction between two molecules tend to pull them together. So these are the two opposing nature because of which matter can be in three phase: solid, liquid, and gas. And then we studied properties of gases, and then we learned that there is macro study and then there is micro study. Macro study means the study of gaseous element as a whole. Yeah. So, and we also looked into gas laws, right? Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and ideal gas equation, which is the combination of all of the laws, right? Yes. Today's class, I'll just do revision about gas laws, and then we'll look into Dalton's law, which is another law for gaseous molecules, and then diffusion or effusion. Okay. So last class we ended up with this equation. Yeah. All of you can type. All of you can type what is Boyle's law, what is Charles' law. Relationship, I want all of you to type. Okay. Relationship. In case of Boyle's law, what exactly is the relationship? In case of Charles' law, what it is? In case of Gay-Lussac's law, what it is? Avogadro's law, what it is? And what um, how to write ideal gas equation. Same equation you can write. Fine. Yes. So now quick. I want all of you to reply. Yeah. Yes. So culmination of all those laws were PV equal to nRT. From that's where we are going to relook upon it, and then we are going to go ahead with our other topics, that is Dalton's law as well as diffusion and effusion in gases. Okay. The same ideal gas equation PV equal to nRT can also be written in terms of density. What is the formula for density? Density is weight by volume, right? Weight in grams by volume in centimeter cube, right? Or it could be in liter also, depends. Yeah. So this PV equal to nRT, in this also there is a volume component and there is a weight component. Remember, number of moles is nothing but weight, given weight by molecular weight, right? So I can say this PV is also equal to W by molecular weight into RT. The same is molecular weight of any gas and weight of any gas is W. Okay, so what I'll do is I'll take volume to one side and molecular weight to the other side, and then I can write Pm equal to W by V into RT, which is also density into RT. Clear? So this is another equation which I am again going to write. This I can rewrite as Pm equal to dRT. Okay, this is also very important expression. Yeah, questions can come on this also. Yeah, I'm not getting any reply. Quick, what is Boyle's law? What is Charles' law? What is Gay-Lussac's law? Yes, Boyle's law says pressure is inversely proportional to volume. Today's my discussion. In the beginning, I will be discussing about this. So I wanted you all to get involved in that. What is the relation between pressure and volume? Pressure is inversely proportional to volume. What is the relation between pressure and temperature? pressure is directly proportional to temperature. Which law is this? Gay-Lussac's law. Provided volume and number of moles remain constant. Okay, here temperature and number of moles constant. Okay, here volume and number of moles remain constant. Similarly, what is Charles' law? Volume is directly proportional to temperature. So volume temperature relation is Charles' law. Volume is directly proportional to temperature is Charles' law. And what is Avogadro's law? Volume is directly proportional to number of. And I also concluded in the last class that the same relation can also be obtained using this ideal gas or ideal gas equation. What I can say, if I take volume to the other side and other factors are constant, let's say number of moles and temperature are constant, then I can say pressure is inversely proportional to volume. And directly when I see that volume and number of moles R is anyway constant, then I can say pressure is directly proportional to temperature. In other case, if pressure is constant, number of moles are constant, I can say volume is directly proportional to temperature. And if pressure is constant, temperature is constant, I can say volume is directly proportional to number of moles. So that's why last class I told that ideal gas equation is the culmination of all the gas laws. Clear? Yes. Today, the yesterday's part which was there, understanding graphs. Yeah. Sometimes graphical type of questions can come. Okay. Instead of temperature being given, they might have given T1, T2 and T3, and they may ask you to find out relation between T1, T2, T3. Is T1 greatest or T3 greatest? So this kind of questions are expected. Okay, and I'll tell you one technique, one procedure, how to approach any such question. Okay, so here the relation is between pressure and volume, and various graph represents graph at various temperature, or relation between pressure and volume at various temperature. Okay, so to understand the relation between T1, T2, T3, here 600, 400, 200 is already given. So I know this graph is corresponding to maximum temperature and this graph is corresponding to minimum temperature. But in general, how to do it? To do in general, what I'm going to do is I'll draw one straight line. Either of them is okay. Either you can draw a line which is parallel to x-axis, or you can draw a line which is parallel to y-axis. Both of them is correct. Okay. And what does this line represent? This line represents pressure is constant. Okay. So if pressure is constant, whatever point you are getting, that is volume versus temperature, right? So here I am getting for temperature, let's say this is T1, this is T2 and this is T3. So for temperature T1, I am getting volume V1. For temperature T2, I am getting volume V2. And for temperature T3, I am getting volume V3. So which one is highest? Obviously, as we go on towards the positive direction of x-axis, the last value will be highest. So V3 is maximum, V2 is next, V1 is next. And what is the relation between volume and temperature? Provided pressure is constant, what will be the relation? Volume and temperature are directly related, right? That's what Charles' law says. So using that law, I can say T3 is also greater than T2, greater than T1. Understood? So this type of question has to be approached in this direction, this way. Okay, so as you can see here, 600 Kelvin is maximum, then 400 Kelvin, then 200 Kelvin. Okay, yes. Fine. Yeah, Sarai, you can type your question as well. I'm only seeing question mark. If you are having any question, please type it. I wish to answer your question. Yeah. Okay. On the other hand, if you say, sir, I'm not comfortable with parallel to x-axis, let's see how it goes with parallel to y-axis. So parallel to y-axis means, what does parallel to y-axis mean? here volume is constant. Okay, volume is constant. So then the relation becomes between pressure and temperature now, right? So at this particular pressure, I am having temperature T3, right? The same convention I'm using T3, T2, T1, and corresponding to T3, pressure is P3. Corresponding to T2, pressure is P2, and corresponding to T1, pressure is P1. Okay, so then which one is highest? P3 is highest, right? So P3 greater than P2 greater than P1. And what does Gay-Lussac's law says? Gay-Lussac's law says that when volume is constant, pressure and temperature are directly related. So we can say since P3 is the greatest, similarly T3 should be greatest, after that T2, after that T1. Clear? Okay. So this is how we understand things graphically. Yeah. So try this one now. Here volume temperature relations are given for various pressure. Okay. So this is the relation that we all have to get. Yeah. How to obtain that relation? Yeah. Again, the similar procedure goes. You keep either volume constant or you keep temperature constant, either of them. Okay, so when you keep volume constant, then you will see that, yeah, this graph has to be little extended, or we can draw a parallel line which is below so that all lines are covered. And then at various P, I have different temperature, right? Yes. So at different pressure, we have different temperature. So this is T4, this is T3, corresponding to P4 is T4, corresponding to P3 is T3, corresponding to P2 is T2, and then corresponding to P1 is T1. So now what is the relation between T1, T2, T3, T4? T4 is maximum, then T3, then T2, then T1. And what is the relation? Here what is constant? Volume is constant, right? Volume is constant. So what will be the relation between P4, P3, P2, P1? I have to refer to Gay-Lussac's law, right? Temperature and pressure are directly related. So if temperature is maximum at 4, pressure will also be maximum at 4th condition. P4, then P3, then P2, then P1. That's how we are getting this relation. Okay. Yes. So this is how you can analyze things. From graph, you can bring out the relation. Clear? Yeah. Last class I had just briefed out. This class I'm just revising everything and making it a little more deeper. Clear? Yes. Try out this pressure and temperature. What happens when you go on increasing volume? Okay. Yes. Which graph corresponds to maximum volume and which graph corresponds to minimum volume? Yeah, this type of questions can come. This may not have been given. They can directly ask. This is corresponding to V1, V2, V3 and V4. What will be the relation between V1, V2, V3, V4? So to do that, you have to use a similar procedure. What is that? Draw a line which is either parallel to x-axis or parallel to y-axis. Okay, I am preferring x-axis throughout so that consistency will be there. And then corresponding to T1, V1, find out T1. Corresponding to V2, find out T2. Corresponding to V3, find out T3. Corresponding to V4, find out T4. Okay, so which one is maximum? T4 is maximum, then T3, then T2, then T1. Right. So again, we have to use Charles' law over here. So T4, since pressure is constant, yeah, that's why as T4 to T1, it is decreasing. Volume V4 to V1, it will decrease. So V4 will be maximum, V3 next, V2 next, V1 next. So as you can see here, this also represents the same thing. Okay, V4 is maximum, V1 is minimum. Clear? Yes. So either you can remember this relation directly or you can get it. Getting to know how to solve it and get answer is the best approach, because the various type of relation remembering would be very difficult. Okay. Yes. Going ahead, let us try to solve one question based on ideal gas equation. 380 ml of a gas at 27 degrees Celsius, 800 mm mercury level, weighs 0.455 gram. Molecular weight of the gas is. So to do this question, we have to first let us write down all the parameters which are given. Volume they are given as 380 ml. Temperature is 27 degrees Celsius, which we can write it in Kelvin. How to write it in Kelvin? Add 273 plus 27, which is 300 Kelvin. Then pressure they have given us as 800 mm, and weight is 0.455 grams. Clear? Then molecular weight of gas is what they are asking. Yeah. So here we have pressure, volume, and temperature. R is anyway universal gas constant. Number of moles we don't know, but we know weight. Right? So first we can find out number of moles, or we can directly substitute in place of number of moles as weight by molecular weight. Since weight is known, I can put that molecular weight, we can find it out. Right. But before doing that, pressure is 800 mm. Right. So 800 mm, we don't have R value for 800 mm. Remember last class we looked at 4 values of R. 8.314, 0.0821, 2 calorie per Kelvin per mole, right? 8.314 joule per Kelvin per mole, and 0.02821 liter ATM per mole per Kelvin. And also there was 0.83, yeah, corresponding to bar, right? But we don't have for mm. ATM we have, yeah, mm we don't have. So what we can do is 760 mm, we know that that's equal to 1 ATM. This is one relation which you should know, all of you. Okay. So 760 mm always corresponds to 1 ATM. So 800 mm will correspond to how many ATM? Cross multiplication we can do. Right. So 800 by 760 I can put in place of pressure. And what will be its unit? Its unit will be ATM. 800 into 1 by 760 ATM. Clear? And volume is given as 380 ml. And R, since I am choosing liter and here I am choosing ATM, I can choose R to be 0.0821 liter ATM. Got it? Liter ATM per mole per Kelvin. Just erase the upper part. Yes. Liter per ATM per mole per Kelvin. Okay. So here volume is 380 ml, which is given to us. Okay. Yes. Once we are aware of all this value, now we'll have to just substitute and try to get the answer. Yes. Substitute all of this in the equation and tell me what could be the answer. Yeah. PV equal to W by M into RT. Yes. Volume needs to be converted to liter because it is in milliliter. Right. Yeah. Any of you would like to answer? Now it has become very simple. Weight we know, pressure we know, volume also we know, R value also is known to us. But remember students, whenever liter ATM is there, R should be 0.0821. Whenever meter cube and Pascal is there, then we use 8.314 joule per Kelvin per mole. Okay, these two are most frequently used. Here in this case, we'll use this. Clear? So remember this. 2 calorie per Kelvin per mole, we know we don't use it more often, whereas these two we use very often. Okay. Yes. So What is the answer for this? Quick. Yeah. What is the answer? 800 by 760 into 380 by 1000, which is conversion to liters, 0.455 by m into 0.0821 into 300. Right. So if you solve ahead, how much is the molecular weight you are getting? What is the molecular weight? Yes, what is the molecular weight? What is the molecular weight? Yeah, anyone got it? Yes? No? Yeah. What is the molecular weight? 28. Okay. 28. Yeah, simple would be 1 and 2. This 400. Only this multiplication happens to be little difficult. That also you can just make it 0.46 and 0.08 into 300. Okay. If you simplify this, 100 and this will be 0.02. Yeah. Two zeros cancel. This will be 0.06 into 0.46. On simplification, you will get 28. Yeah. Yeah. This 1000 also will go here. It becomes into 1000. Fine. Yes. So going ahead, calculate the temperature. This is a little bit variation in again the ideal gas equation only. Calculate the temperature of 4 mole of a gas occupying 5 decimeter cube and 3.32 bar. So here since bar and decimeter cube is there, we'll use 0.83. Yes. Yes. So number of moles is given, volume is given, and pressure is also given. They are asking us to find out temperature. Yes. Quickly tell me answer. Tell me the answer. Yeah. Any one of you? Quite direct. Let's see. It should not take more than 30 seconds. These are easy level questions. Right? Not take more than 30 seconds. Yes, what is the answer? Quick. Idishri, Sarayu. By the way, Sarayu, you can tell what was your question. I didn't get. Yes. Yes, what is the answer for this question? We need to use PV equal to nRT. Right? Hmm. Substitute everything. Yes. Yeah, you all should be very quick. This is like more than allotted time for any question. Yeah. So P is 3.32. You need not to change any of their units because R is also in bar decimeter cube. This is also decimeter cube and bar. So you need not to change. You can put directly P and V, and equal to N is given 4. R is given 0.83, and temperature you have to find out. So 4 into 0.83 is 3.32, and 5 into 3. 32 into temperature. Yes. Yeah, this one thing has to be 0.083. Okay. Make that one chain. It has to be 0.083. Yes. So it will be 0.083 into 4, which is 0.332. Okay. 0.332. And if you simplify further, you will get temperature to be 50 Kelvin. Yeah. So 3.32 into 5 divided by 4 into 0.083. Solve that, you will get temperature to be 50 Kelvin. Yes. Now let us look into density type of question. If the density of CO2 at 100 degrees Celsius and 800 mercury pressure would be. Yeah, here temperature is given to us and pressure is given indirectly. Again, you have to convert it to direct, right? ATM. From you should convert it to ATM by dividing it with 760. Sorry. Yes. What will be the answer? Yeah, I want answer from all of you. The relation is PM equal to DRT. This is what we did today, right? PM equal to DRT. Use this and tell me the answer. They are asking density of CO2. So molecular weight is known, pressure is known, temperature is also known. R you have to choose wisely. Which R will you choose? And tell me the density. Yes. Yeah. No one. Quick. Yes. What is the answer for this question? Yes. Your density unit will depend upon what R unit you choose. So if you choose R unit wisely, you will get density in a proper manner. Ideally, when density is given, you can use R to be 0.0821 liter ATM per Kelvin per mole. Okay. Yeah, this is the unit which you can use um, for density type. Yes, no answer. This question should not take more than 30 seconds, students. You have to be quick. You can approximate even. Since the values are having more difference, you can safely approximate to get the answer. Okay. Yeah, no answer. Yes. What is temperature in Kelvin? It's 373 Kelvin. 100 plus 273 just 373 Kelvin, and pressure is 800 by 760 which we did last time, right? And molecular weight of CO2 is 44. And usually we choose molecular weight in grams, and whatever density we get, that also will be in grams, right? Yeah. So then I'll substitute everything. Density equal to PM by RT. So if I put everything, it will be 800 into 44 by 760 into 0.0821 into 373. How much will this be? How much will this be? Yes. How much it will be? You can approximate 0.0821 to be 0.08, and then you can cancel out 100 and 0.01, then 760. Yes, it will be 4400 by 7.6 into 373. Yeah, 7.6 into 373, we can do multiplication, or we can directly divide this and this. 373 1, and then 67 670, which will be 11 point somewhere around 8. So this will be 1, and this will be 1 point around 5. right? It will be 1.5 because 7 into 1.5 is 10.5. So 7.6 into 1.5 would be around 11.8. So it will be somewhere around 1.5, right? So if I look at the answer, it will be 1.5124 gram per liter. So just erase and look into the solution. It is 1.5124 gram per liter. Okay, so this is how we can solve this kind of question. It should, however, it should not take more than 30 seconds. Yeah. Yes. Yeah. Now let us look at Dalton's law of partial pressure. Yeah. This is about ideal gas equation and the application, few application type questions which are expected in JE as well as NEET. Now we will look into Dalton's law. Okay. Yes. So what does Dalton's law say? Dalton's law says that the total pressure in any gas will be equal to sum of partial pressures of various gas involved in that mixture. Right. So if say I have a sample which contains only A in it, A could be oxygen, let's say, then the pressure exerted on the surface, yeah, pressure exerted on the surface would be only corresponding to oxygen, right? However, when there is another present which exerts a pressure PB on its surface, yeah, which corresponds to uh, substance B, maybe H2 or so. And let's say if I mix both of them, H2 and O2. Okay. So then the two mixtures which are present, H2 as well as O2, are also now going to exert some pressure on the surface. Right. But this pressure will be, why does pressure exert? Why does gaseous molecule exert pressure? They exert pressure because they have that randomness in them. This gaseous molecule want to move here, there, and if you are keeping some lid or piston on top of it, then they will tend to push that lid or piston upward, right? So that's why there is some feel of pressure on the piston or lid. Okay, so if say a mixture contains H2 as well as O2, to the proportion H2 and O2 is present, to that proportion they are going to exert some pressure on the lids, right? So hence Dalton's law says that the total pressure will be the sum of this pressure as well as this pressure, okay, when they are mixed together. Is that total pressure exerted by the mixture of gas is equal to the sum of partial pressure of each gas. Since we are mixing it, it will not exactly be PA and PB. However, partial pressure into that. Okay. Na by Na plus Nb and Nb by Na plus Nb. That's equal to total pressure. Got it? Yes. So that's what is Dalton's law stating. And that's quite logical also. The total pressure on the surface of any gaseous mixture will be equal to the partial pressure, the pressure exerted by H2 alone and the pressure exerted by O2 alone. Right? So if the proportion is like what is say 1:2, then pH2 into 1 plus 2 into PO2 will be the total pressure. Right? So that's what is Dalton's law stating. Okay? But it is only applicable for non-reacting gases. The gases react with each other, then pressure is not just summation of two mixtures. Right? Yeah. So yes, so I can say total pressure is equal to, yeah, Na RT by B. Whereas this Na plus Nb, we are not going to put because when we add automatically, this represents the total pressure, total number of moles into RT by B. Okay, yeah. Basically, there was initially Na plus Nb present in the numerator as well as in the denominator. That's what it means. So we know that pressure is total number of moles into RT by B. So that total number of moles and mole fraction Na plus Nb, that factor of mole fraction got cancelled. Clear? So that's why it is Na plus Nb into RT by V. Clear? Yes. So you can say that Pa equal to mole fraction of A into Pt and Pb is mole fraction of B into Pt. Clear? Yeah. So that's how we can find out partial pressure of each gas. Let's look into one question. Equal weights of methane and oxygen are mixed in an empty container at 25 degrees Celsius. What is the fraction of total pressure exerted by oxygen? So equal weights of methane and oxygen are mixed in at 25 degrees Celsius. They are asking fraction of total pressure exerted by oxygen. So what are they asking? PO2 by PT. Right. This is what they are asking. Fraction of PO2 with respect to total pressure, which is nothing but mole fraction of O2. Right. They are asking just this. We need not to find out any other thing. How to find out mole fraction of O2? This is nothing but number of moles of O2 by number of moles of O2 plus number of moles of methane, which is CH4. Yeah. Since equal weights are there, let's try to find out number of moles of O2 and number of moles of methane. Then by substitution, we'll get the answer. Right. So W by molecular weight of oxygen is 32 and number of moles of CH4 is W, same weight W by 16 because they are equal weights. Right. So I'll substitute that over here. I'll get W by 32 divided by W by 32 plus W by 16. Clear? So upon simplification, W by 32 in the denominator it will be W plus 2W by 32. So you can simplify it and find out P of O2 by Pt is equal to 1 by 3. Got it? So the fraction would be 1 by 3. Because 32 and 32 will get cancelled. Right? Yeah. Try another question. Mixture of gases at 760 mm mercury contains 65% N2, 15% O2 and 20% CO2 by volume. Then partial pressure of each gas in mm is. Yes. Yeah, this question may seem difficult, but what we actually need to use is PT equal to PA plus PB plus PC. Right? In this case, PA is N2, PB is O2, corresponding to O2, and PC is CO2. Okay? Yes. And let's say if the total pressure is X, you say the total pressure is X. Yeah. As of now, I'll consider it to be X. And then we'll, for specific in case of 760 mm, let's try to find out. Okay. PA would be chi A into PT. But what is chi A? Mole fraction of A. Here A is N2. So mole fraction of A is 65%. It could be 65 in percentage also. Percentage by volume is same as mole fraction only. Okay, you can take that for granted. Why? It's because of Avogadro's law. Okay, percentage by moles, percentage by volume will be same. Okay. Yes, that's due to Avogadro's law. Okay, so I can say PA would be 65% of PT. PB would be 15% of PT and PC would be 20% of PT. Okay. Now since PT is given as 760 mm, I can put that as 65 by 100 into 760. And this I can write as 15 by 100 into 760. And this will be 20 by 100 into 760. So try solving it and tell me the answer. Wait. Yes. Yes, how much it will be? Even here, you can do a quick calculation. Yeah, roughly you can get some number and check it. Okay, need not to perform all calculation. 20 by 100 into 760. I can directly cancel out two zeros, and 2 into 76 by 1, which is 152. So 152, 152. Here PB is 15 by 100 into 760. Again, I can cancel out 20 and put one, move to two decimals. 15 into 7.6, which will be somewhere around 110, right? Because 15 into 7 is 105, 15 into zero point 0.6 is 9. So 105 plus 9, somewhere around 112 it will be. Okay. Yes. What about 65 by 100 into 760? Even this you can directly calculate, or you can do like this also. 760 minus 112 minus, here we got it to be 152, minus 152, right? Because totally it should be equal to 760. Based on that, I can use this and I can tell it will be 264. 760 minus 264 is 494, around that, right? Yeah, 496 maybe. Okay, so which values are very near to it? The option C, right? So the answer would be option C. Let's look at the solution. Partial pressure of N2 will be 760 into 65% of 760, which is 494, 114 and 152. So answer is C. Next, let us look into diffusion and effusion. Okay. So what does diffusion mean? Diffusion means the spreading of one gas in another. In case of gas, I can say spreading of gas in another gas. Okay. In case of this liquid, the water, the color gets diffused. That's why you can see various color, the color getting spread everywhere, right? Yes, if you take a sponge and if you put ink on it, you will see that it diffuses, right? It spreads. Okay, that's what is diffusion. Whereas, what is the effusion? Effusion is just moving out. Okay, effusion is moving out and diffusion is entering in. Right? Yes, it's almost similar. Only thing is that the opposite of each other. They are opposite of each other. The ability of gas to spread and occupy the whole available volume, irrespective of other gases present. The container is called diffusion. Effusion is the process by which a gas escapes from one chamber of a vessel through a small opening or an orifice. For example, if I open this, the gaseous particles which are there inside will start moving out. That could be the example for effusion. Yes. And there is something called as rate of diffusion, which is defined as volume diffused by time taken. And it can also be number of moles diffused. Sometimes this kind of details will also be given. Okay. In place of volume, moles may also be given. So number of moles diffused by time taken. This can also be called as rate. Okay. Yes. So Graham's law gives the relation between rate, density, and molecular weight. Okay, so he says that at constant pressure and temperature, rate of diffusion of gas is inversely proportional to square root of its density or molecular weight. So it's inversely proportional to square root of D or square root of N. Okay, or in general, I can say R1 by R2 is equal to root of D2 by root of D1. Okay, so square root of D2 by D1, or we can also say this as square root of M2 by M1. Okay, now let us see when the pressure increases. Okay, let's say in the same container there were molecules wanting to come out, and let's say somehow inside pressure increases, maybe increased, maybe you supplied some heat or something, but did some activity because of which pressure increased. So then if you try to remove this lid, what will happen? The air molecules will come out very faster, right? So from this I can say rate is also proportional to pressure. Okay, so rate of diffusion of gas at constant temperature. Yeah, we cannot do it by supplying heat. Temperature should be constant, is directly proportional to its partial pressure. Clear? Yeah. So to account for that, I can say rate is proportional to P, and we already know rate is inversely proportional to square root of M or square root of T. From this, I can combine both of this and write it as R1 by R2 equal to P1 by P2, because they are directly related, into square root of M2 by M1. Or I can also say it's R1 by R2 equal to P1 by P2 into square root of D2 by D1. Got it? Yes. So why are we studying this? There are various applications, out of which few important ones are detecting the presence of marsh gas in mines. Okay. This can be understood by a technique of diffusion, separation of isotopes such as U235, U238 by different diffusion rates. Yeah, their diffusion weights will depend upon molecular weight, right? So based on their diffusion weight, we can differentiate two different isotopes. Okay, and we can find out molecular weight of unknown, yeah, as well as vapor density. This or this of unknown by knowing the other one. Okay, so let's say both R1 and R2 is known, and one of the molecular weight or vapor density is known. Then we can find out vapor density of other as well as molecular weight of other. Okay, so these are few applications of diffusion. Okay. And questions can also come on this, like finding out the molecular weight of unknown compound. Okay, we'll solve one such question. Okay. Yes, here is one question. The find the ratio of rate of diffusion of oxygen gas at 4 atm and hydrogen to hydrogen gas at 2 atm. Yes. What could be the answer for this? What will be answer? Oxygen gas and hydrogen gas. You have to find out ratio. That means RO2 by RH2 you have to find out. Pressure is different. For both of them, pressure is different. And molecular weight is also different. So can you tell me the answer quick? What will be the answer? What will be the answer? Yeah. Direct formula. Right. So it is PO2 by PH2. Yes, directly related into root of inversely related. So it is MH2 by MO2. Right. Yes. So if we can substitute everything, PO2 is given as 4, PH2 is given as 2 into molecular weight of H2, we know it is 2, molecular weight of O2 is 32. 1 and 16, root of 1 by 16 is 1 by 4. So we'll get 4 into 1 by 4 by 2, 4, 4 cancel. Answer will be 1 by 2. Clear? Next question. A bottle of dry ammonia and a bottle of dry hydrogen chloride. Okay, something is happening. Okay, connected through a long tube are opened simultaneously at both ends. So there is one place there is dry ammonia, another place there is hydrogen chloride, dry hydrogen chloride, and now they are connecting it using a long tube. Okay, and both are opened simultaneously. The white ammonium chloride ring first form will be at the center of the tube near the hydrogen chloride bottle, near the ammonia bottle throughout the length of the tube. So to understand this, I'll give you one hint. The reaction is NH3 plus HCl giving NH4Cl. So this fellow is this white ammonium chloride. So there is two places one place where ammonia is there, another place where HCl is there. Okay, and they are connected through a long tube whose ends are opened at one go. Okay, both are opened simultaneously. So then this fellow will come from here and this fellow will come from here. At one point, they will form a ring, white ring. Where exactly they form a ring is a question. Yes, just think about it and tell me the answer. Another hint that I'm going to give is R is inversely proportional to square root of molecular weight. So this is another hint to understand who will go faster. Whoever goes faster, opposite side of it, you will see a ring, right? Let's say if ammonia goes faster, ammonia will go near to HCl much faster than HCl coming near to ammonia. Right. That's why a ring may be formed near HCl if ammonia has lower molecular weight. You can understand rate in this manner also. Whichever is heavy, whichever molecular weight is more, they will go very slow. Their rate will be slow. Okay. Whichever are not so heavy, whose molecular weight is less, their rate will be faster. For HCl, molecular weight is 36.5, whereas for ammonia, it is 70. So 70 is less than 36.5. So ammonia will try to go faster towards HCl. That's why you will see the white ring near hydrogen chloride bottle. Got it? The answer is 2. Next question. Two gases A and B having the same volume diffuse through a porous partition in 20 and 10 seconds respectively. The molecular mass of A is 49 U, molecular mass of B will be. Okay. So both are in almost identical type of vessel. Okay, they have same volume and there is some porous media on top of it. Okay. So let's say this is some vessel. Both are there in the same kind of vessel and um, here there is porous outlet. One diffuses at 20 seconds and another diffuses at 10 seconds. One which diffuses at 10 seconds is B and 20 seconds is A. For this, molecular weight is 49 U. They are asking for this, what is the molecular weight? Okay, so volume is same. Yeah, so VA equal to VB, I can say. What will be RA? RA is VA by TA, right? Number of volume of gas divided by time taken, right? And RB is VB by TB. So what will be RA by RB? VA by TA into VB above will be TB, right? Because VB by TB, TB can go up, which will be equal to, this will be equal to pressure. There is no difference. Pressure is same. So I can directly use, it will be MB upon MA, right? MB is what I have to find. MA is already given. So VA, VB is same. VA equal to VB. So I'll cancel out. TB by TA. What is TB? 10. TA 20 equal to root of MB by MA is given as 49. U means atomic mass unit. Okay, so just cancel out and square it. It will be 1 by 4 equal to MB by 49. What is 49 by 4? It will be 12.25 U. Okay, so answer will be 12.25 U. Fine. Yes. Hope you are understanding this. This kind of questions are expected. Okay. So ideal gas means those questions which are graphical type as well as density type. Yeah, such kind of questions. And in rate of diffusion, yeah, fine. This kind of questions can be. Next question, 100 ml of O2 gas diffuses in 10 seconds. 100 ml of X gas diffuses in T seconds. Gas X and time T can be. So in this question, since two parameters are known, there can be multiple possibilities. There can be multiple possibilities. Okay. So in such case, what you can do is you have to cross validate all the options. Okay. So whichever are coming through, those all will be the answer for this. Fine. Yes. So let us write down first R O2 as well as Rx. Our O2 is volume of O2 by time taken, which is 100 ml divided by time taken is 10. I can say 10 from same unit. I will keep so it will be 10 units. Okay, and Rx will be 100 ml by T, some T. Okay, so first let us simplify it before substituting. So it will be RO2 by Rx, which will be 10 by 100 upon T. Or I can also tell this is T by 10. Okay. This should be equal to molecular weight of X by molecular weight of O2. Right? Should be equal to molecular weight of X by molecular weight of O2. Molecular weight of O2, we already know it is 32 equal to T by 10. So now let us start putting all the options in it and check whether this relation is coming true or not. So for first one, H2 and 2.5 seconds. So T is 2.5. And just make space for writing the answer. If you wish, you can pause and copy down this. Yes, for first option, for first one, it will be MH2, which is equal to 2, and T is 2.5. So if I put both of them, it will be 1 by 4 equal to root of mx, which is 2 by 32. 2 by 32 is 1 by 16. Root of 1 by 16 is 1 by 4. So this is coming correct. So this option is correct. What about second one? Second one is molecular weight of SO2. Telling it is SO2. So molecular weight of SO2 is how much? 32 plus 32, which is 64. And time taken is 60. So if I put that, it will be 16 by 10 equal to root of 64 by 32. 2 and 1. Root 2 is not 1.6. Yeah, it's not 1.6. So this is not the answer. 1.414, right? Root 2. It's not correct. Third one. Molecular mass of carbon monoxide. How much it is? 12 plus 16, which is 28, and time they are telling it is 10 seconds. So if I cross validate, 10 by 10, which is 1, it's not equal to root of 28 by 32, obviously. So this is also not correct. What about this? 4 by 10, time given is 4. I'm directly putting it. Helium molecular weight is 4, and this is 32. So 4 by 32, which is 1 by 8, and this is 2 by 5. No way 2 by 5 equal to root of 1 by 8, right? So I can say this is also not correct. So only answer is H2 and 2.5 seconds. Okay, so this was about diffusion as well as Dalton's law. Okay, with this we are done with macro study. Okay, so just go through everything, and if you are having any doubt, you can just put in chat box so that we can have a discussion on it, and I'll also get to know how much you have understood. Okay, yes, so hope you understood this concept of diffusion as well as Dalton's law and part that we learned yesterday. Okay, so we'll end here. Thank you.